Okay, fantastic. Let's get started. Um, okay, guys. So, the whole purpose today is basically, um, so number one, we're gonna get like a new play reader, right? So I'm still like kind of negotiating with the company to see which one we're gonna get. But nonetheless, I feel like, when I talk to people, I think we really should come together and discuss, how to use PlayRadar. I feel a lot of times people just use it, they just copy a protocol from whoever established that, click a button, then run. And that's not the way it should be, right? So I think in our group, I really want everyone, that's my requirement. I think everyone from my group should be able to create your own protocol. You should never copy just other people's protocol. You should go, when you run an assay, you should just click like new experiment or new protocol and establish every step by yourself. Okay. Never ever copy other people's protocol. Number one, you don't know, like for example, the person who created the protocol, they may change the protocol. Or maybe like some other people change the protocol, save it, right? Override the original protocol. And when you run your experiment, you assume everything is right, but then, it can probably get messed up. So you should that's another thing, right? So you should understand every step, every parameter, what it means. And then you will be able to optimize your assay instead of just blindly click a start button. That's not that's not what I want. Okay. So, right now we have this one, right? We have this which is H1, the Biotek H1 play reader, right? So it's pretty good play reader. I really like it. Um, you know, we we've been using this for like over 10 years. I just want to make sure it's recording. Erica, can you confirm it's recording? You should be able to see.
Yes, it's recording. It started at the beginning.
Okay, great. Yes. Okay. Yeah, so H1 has many different functions which I'll go through. Just make sure, probably most of you guys already know, but I hope everything is clear. And we are also looking at other play readers right now. Like one is from the BMG Labtech called the ClarioStar, and they have another version called the ClarioStar. And I'll just kind of go through the features they have. A couple of weeks ago, right, or last week, we have the Biotek Neo 2 demo. The Neo 2 essentially just like H1, but it's a more advanced version of H1, right? So it's a lot faster. It can read a 384-well plate in 11 seconds. So that's like super fast, right? Actually faster than any of the BMG plate reader. So that part is good. And also, I think for the Neo 2, they have the new function which you can tune the bandwidth of your monochromator. However, Biotek instrument has some other deficiencies, which we'll talk about that next. Okay, I just kind of list everything here. I want to make sure everyone understand, right? So here are the potential detection modes for like play reader, right? Absorbance. So what is absorbance? You just, it sounds simple, right? So, but basically, what you do is you shine light from either bottom or top, and then you detect on the other end, right? So the question here is, can you, like for example, you want to measure DNA or protein absorb concentration at like 260, 280? Can you use a regular plate to do that? Maybe I should ask a new student. Suggest me. You think can you use a like regular 96 well plates to measure 280 to 60 absorbance?
No.
Why?
I think in the video you said something about the lower you go, 67 or something.
Yeah. Yes, that's exactly right. So I mean, what is plastic? Plastic is also chemicals, right? So it's the one we commonly use is called polystyrene. Styrene has phenolene. Phenolene absorb very strongly, 254, right? So that's so essentially those plates are good for longer absorption. I would say about like 350, 360, 400 will be safer. But in terms of the UV range, that's definitely not a good idea for absorption, right? So you have to understand, right? So for absorption, it needs to go through the whole solution, right? Go through the bottom. But on the other hand, if you're measuring a fluorescence, then probably it's okay because you don't, you can do the top rate and you don't need to go through the bottom, right? So you need to really understand the whole physical process. So if you really want to do absorption, right, in 96 well format or 384, what can you do like in the UV range? Do you guys know? Did I mention that in the video? I don't remember. Yeah. So what you can do is actually can buy those expensive plates, which is transparent in the UV range. Okay. So those are specialized. I think Harmon, you have those, right?
Yeah, I should have some.
Yeah. But I mean those are pretty expensive. So basically I think we just use them well by well sort of, right? So but we do have those if you really need that. Okay. So that's something I wanna make sure everyone know. And on our H1, when you measure absorption, actually it measures like one wavelength by one wavelength, like that. But actually the new plate radar looking at actually it's I think it uses grating or something like that. They can measure the whole full spectrum just in 1 second, like one shot, very fast. Yeah, so in terms of that, it's pretty cool. But the interval. Oh, you mean the resolution?
Yes.
Of, I mean, they said they can go down to 1 nanometer. Yeah, and actually it's not that surprising because when I was a student, like the old plate reader we had in the lab from HP, they were able to measure absorption just in 1 second, like single shot. I think they have, I don't know how exactly it works, but that's just the way it works. They probably have a, like CCD camera or something like that.
What's the cost of reading that fast? Is there a lower sensitivity? Is there any drawback?
Yeah, I don't know. That's a good question, right? I definitely think that I agree with you. I think the cost of reading fast is probably sensitivity because my understanding is I mean, if you read that fast, what you need to do is, I mean, you give a white light, you need to separate the white light, right? Then eventually you need to detect that. I mean, the easiest thing to do is using a CCD, sort of, right? But those are not as sensitive as PMT for sure. But PMT cannot discriminate the wavelengths, right? So if you have a PMT, like you can only like just let certain wavelengths go through, measure that, and then measure again, just like Biotek does. So that's actually a very good point. That's why I believe Biotek make the claim. They said they can go to like 0.0001 absorption, something like that, 4 OD or 5 OD. I don't remember. I'm pretty sure the one we have actually can go to 4 OD because we tested that before. Maybe their newer one can go even higher, but I think the faster scan probably had a cost of the sensitivity. Yeah, that's a good point. Okay, so that's the absorption, and the next one is people come to use is fluorescence, right? Fluorescence, it can actually do both the so-called top read and bottom read. So, when you want to use top or when you want to use bottom, right? So the top read, in general, top read is more sensitive. Why? Why? Anyone? You think top read is more sensitive? Just take a guess.
Open-ended.
Open-ended, yeah. But what's the bottom read? I mean, bottom read is what? You have to go through the plastic, right? Yeah, that's exactly the reason. So you go through, one more layer, you lose signal, right? So, however, top read also, when you want to do top read, another very important thing is you should do the Z height adjustment. That's something I really want to emphasize over again, because when you do this kind of fluorescence, you need to shine light into the solution and then detect at another angle, right? So this sort of two, the detection and the excitation should meet somewhere in the solution. So if you change your focal point, if you make the focal point too high, you don't really see the solution if your volume is low, right? So also sometimes when you adjust the volume with your assay, you definitely want to readjust your Z value, because you may miss your you may miss that. So if you change anything in your assay, for example, volume or whatever, you should readjust all the parameters and make sure that works. So for our the H1 plate reader right now, I believe the bandwidth is 8 nanometer. I didn't check, but I think that's the number. So it's kind of narrow. That's why it also has a filter function. The filter function, you can just go with as big the bandwidth as you want, right? So that's why in general, filters give you higher sensitivity, right, than the monochromator, at least on the on our H1 system. So you should know, like when you use monochromator, actually it's convenient, but you sacrifice your sensitivity. On the other hand, on the the newer instrument BMG, what they have is really pretty cool. You can adjust the bandwidth. For example, you can go up to 100 nanometers. That's actually super wide. And with that, you can sort of use that to mimic filters. You don't really need any filters, to enhance the sensitivity. But at the same time, it gives you the filter option to do that. If you want to say go, above 100 nanometers, you can do that. This ClarioStar actually is a higher end system, but this higher end system only allow filters, not like monochromators whatsoever. So in that sense, it's a little bit limited, but has higher sensitivity. We'll talk about that later. So that's fluorescence. I think we don't do a lot of fluorescence, but I think, like the EF7 assay, right, and E-runs, and those are like fluorescent based assay. I think Min is also working on those 8R1 assays, which is based on fluorescence. So, and then the next one will be fluorescent polarization, right? So what is fluorescent polarization? Lex, do you remember still what is fluorescent polarization?
Yeah. This one study how whatever it
So should you label the fluorophore on the protein or on the small molecule?
you're going to be based on this comment.
Use that protein?
No,
Small molecule or protein? Is that right? Small molecule or protein?
Small
Yeah, that's right. Yeah, because small molecule rotates fast, right? Then you wanna see a big change and you wanna label on the small molecule. Once it binds to protein, you really change the rotation, right? So yeah. For this kind of application, it's essentially just filter based. Yeah, both of these are, I think all the instruments need to use filters for this. And I think on each one they have this, you have to put polarizer, like in front of the excitation source. On the BMG system, my understanding is actually they have polarizer right in front of this excitation source. I'm not quite sure, but anyway, they will use filter for sure. But the problem here is if you are measuring steady state fluorescent polarization, it's okay because it's gonna be there, right? So you can switch your polarization like either parallel or vertical. You can switch that, no matter how much time it takes. But if you are trying to use FP to measure kinetics, right, the binding kinetics, like this switching time delay, if it's on the time scale of the binding process, then you will bias you will get wrong results essentially, right? You don't measure the two emission at the same time point. So that's why I think for the BMG, what's this? This ClarioStar, they have the dual PMT system. So essentially you can measure both horizontal and vertical at the same time. So then you'll be able to measure binding kinetics that way. So definitely Biotek, the Neo 2 has the same capability, the dual PMT function. The dual PMT is essentially very useful when you measure kinetics. So other than that, it's not that useful. Sure.
Because the reason is person I found some of the things.
Mhm.
So I would like to trace everyone in there. So I have a thinking in my head that, so for example, we do those sets on it.
Well, mhm.
I'm thinking if there is a part of the system that we can actually have them for the thing. So for example, if I need to just get, so for example, I'm living a circuit pattern on the set that is converted to the third one, right? I just want to know if this pattern are present in the cell. I'm thinking instead of using flow, I could go to that now. You can get that. If that is the use of that, that's correct.
I see what you're saying. So you're trying to label cells, right? With the dye labeled antibody.
Yeah.
And so you label the cell surface, then can you read out? You probably need to wash away the unbound dye, right? Or can you really see that on plate reader? The answer is hard, very difficult. The reason for that is number one, if you use adherent cells, adherent cells, they're just monolayer.
Yeah.
That's going to be very challenging for plate reader because you think about your focal point, right? So the cells only maybe like 1 micron thick or something like that, or maybe less than 5 or 10. Yes, that's the thing, right? So number one, for adherent cells, it's difficult, but you could try this bottom rate. It might work. Most likely it won't. But then you can lift them off the plate, like I said, right? So you can make them as suspension cells. We tried that before. Not really exactly the experiment you propose, just through the surface area. We actually try to load cells with our GSH probe. Those are super bright dyes. And so on the when we use adherent cells, it didn't work. But when we make them as suspension, you start to see signals, but still it's weak. And so then considering if you just label the cell surface, your amount of dye there is a lot lower, right? And that's why I think it'll be highly challenging to do that. With that being said, we have another instrument actually, which is the imaging reader, and that might work. That might work. Yeah. So I mean, if you want to use that, Xiaoli can teach you how to use it. Yeah, Harman.
I just had another point going through the benefits of dual PMPs. I think, my impression is that it's not actually only for kinetics. Because in any ratiometric measurement, sometimes and often actually with RH1, you can encounter some baseline drift over time. So let's say I take, 2 readings, 2 different wavelengths, but they're measured a minute and a half apart. Sometimes during that period of time, some baseline drift in, let's say, the excitation wavelength, or not the wavelength, the excitation intensity, can change that ratiometric measurement, particularly at high concentrations. I believe I've observed this in my field. So actually just measuring those at the same time point is also good to counter any baseline drift that you can.
Yeah, I totally agree. I mean, the dual PMP, especially for the ratiometric measurements, that'll be the way to go, right? So it will give you a smaller error bar, and yeah, so that's why I think we have to get one system like that. Yeah, it will definitely dramatically, I don't know whether dramatically, but it will definitely increase the data quality for sure. Yeah. Okay, questions? Good. So luminescence, actually, luminescence is the cheapest thing, the easy thing to read. The instrument luminometer actually the cheapest one. So if you want to go with very cheap instrument, luminometer actually costs maybe like a new one, even like less than 10,000, 15,000, something like that. Promega is actually trying to make one cost less than 5,000. And then you can stick into the incubator and then monitor the nanobread kinetics, over time. But anyway, for luminescence, you don't need anything. You just need a PMP. That's it, right? So it's like the thing, like cells or whatever reaction will glow, and you just make sure it's dark, and PMP read out the signal. That's it, right? So it's very easy. And then the nanobread is essentially another version of luminescence. But this time, instead of collecting all the light, now you collect, specific wavelengths, right? So 450 and 610, right? So then you do ratio. The same thing. I think if you have dual PMT, you probably get better, better data, especially I think for the nanobread. Because nanobread, you add substrate and the signal actually decays over time. It's it's not that stable. But anyway, that's like nanobread is sort of, we do that all the time, right? So one question I have is for the nanobread, if you look at the background is what? Actually, the 450, I mean, luciferase emit at 450, but actually the emission band is super broad. It can, leak into the 610 channel. So that's why the ratio sometimes difference is not that great. Yeah, we were thinking, can you really find a way to make the, the nano-look emission narrower, or blue shifted? Actually, then I found a substrate called a deep blue sea. Yeah, interesting, right? So actually, that one, the substrate, if you like, I think if they use vanilla luciferase similar to nano luciferase, they can emit around 400 nanometer instead of 450. So that might, I don't know, it might, improve the signal to noise. Who knows? But we can try that.
Well, can you just narrow the bandpass of the
You narrow.
field? Maybe the signal will be a bit lower, but you decrease the longer.
Yeah.
Another kind, it's the symmetry or asymmetry in the field. If it can be a symmetry, maybe you can
Yeah, it's measured.
decrease the
You mean like instead of using 610 long pass filter, we use 620 or 630, right? So you go, yes, that's one possibility. But then at the same time, like you said, you probably lose the dye signal. But anyway, so that's just something to think about. Yeah, maybe, you know, worthwhile trying that deep blue sea or whatever. No, actually, it's very old substrate. People never pay attention to that. Yeah, yeah. It's, you know, the funny thing is, if you look at structure of that substrate, essentially, on the fluoromazine has like, you know, different ring substitution there, right? So I think 3 rings. In the deep blue sea, that substrate essentially all the rings become phenyl ring. So they don't have any electron donating groups whatsoever. So that's probably why they make it, you know, like higher wavelengths. I mean, like shorter wavelengths, higher energy. I don't know. But anyway, that's something we can worry about later. And then the TR fret, right? Oh no, sorry, time resolved fluorescence. So what's the difference between time resolved fluorescence and TR fret, right? So we do TR fret all the time. Time resolved fluorescence essentially, you just think about one experiment. You know, actually we have done this experiment in the lab in the old days. When we work on these polymers, one way you can label the polymer is you can label the polymer with terbium, for example, you know, terbium ligands, right? Then load terbium in there. And then you inject this terbium labeled polymer into blood. And you take blood, you measure the pK, right? So you can measure the pK of that polymer. And then when you measure the pK, I mean, when you try to quantify the amount of polymer, you can directly just do time resolved fluorescence. You excite at 340 and then wait 100 microseconds and measure the fluorescence. Because at that time, all the background fluorescence from hemoglobin, whatsoever, are going to be gone. And you can achieve super sensitive reading, actually. Yeah. So, you know, that's basically how you can apply this time resolved fluorescence as a way to label it, right? So based on their instrument specification, you can go down to like femtomolar concentration. Yeah, 80 femtomolar or something like that. So pretty low. Okay. Then the TR fret, right? Time resolved fret. We run that all the time for binding assays. You know, these are filter based right now. For the newer, I mean, the high-end instrument like ClarioStar, what they have is actually, instead of using this xenon lamp to excite the terbium or the, you know, lanthanide, they use a laser specifically at 340, 337 nanometer. So, you know, the laser, the key difference versus the xenon lamp is it has a lot higher intensity, right? So you generally will see a lot higher signal there. Yeah. You know, another thing is, if you think about this TR fret experiment, I don't know whether you guys pay attention to this or not, but like last time, I know like when Ran tried to establish this binding assay, you try to increase your dye concentration, right? There, I mean, like you have terbium label BDK, you use dye label the cereblon, you try to titrate the cereblon concentration. But I don't know whether pay attention to that. At very high dye label cereblon concentration, you start to see a lot less 495 emission. 495 is a terbium emission, right? That emission should be a constant because, you know, that's the way it's supposed to be. But if you see less emission in the very high concentration of dye, what does that mean? It's not quenching. What is hook? I know, yeah, it's like going up. No, it's not hook. That sounds like a fancy word, but it's not. So why handphone? Why? When you use a high concentration dye,
It's a lot of 30 nanometer energy was observed by another protein or another dye.
Yeah, exactly. Say it again.
A lot of energy of 330 nanometer excitation energy was absorbed by another reagent.
Biotek,
Yeah,
Yeah.
the tracer.
but still no quencher, right?
It's not called quenching. I mean, quenching,
Yeah, it's
by
not-
definition, quenching is the dye, I mean, the terbium will excite, absorb the energy, then this will quench the fluorescence. Basically, this is actually called the inner filtering effect, by the technical term. So what it means is, so when you have light coming in, right, so everyone has an equal chance to absorb the light, right? So, but if you have a lot of high concentration of your dye, those dye will absorb those short wavelengths.
You mean the
Like-
tracer absorb the 340,
Yes,
not the emission of the 340.
no, directly absorb 340.
Oh, directly.
Yeah, because although those dyes, they claim they absorb like 480, whatever, every compound absorb in a very short wavelength range. That's the way it is, if you measure this full UV absorption. So we should definitely pay attention to this, right? So especially when you use high concentration tracer, and you may have this kind of inner filtering effect. And yeah.
Mineral compound is FHI that also affects the terbium.
Yeah, I know, but that might be a different story. Yeah, I don't know. Yeah, but have I what? Yeah, it essentially applies to everything because as long as the dye itself has strong absorption at 340 or absorption at 340, right? So it's gonna affect the light getting absorbed by terbium. That's why I think I don't have the data, but I would guess if you have a laser-based excitation source, you will have less of this kind of problem.
Aren't you taking the measurement after a delay where you can speed the excitation?
No. The delay is about the emission, right?
Yeah, well, my question is how do we observe it, right?
How do we
How
observe?
do we know that the 340 is being absorbed if we're not making an observation on the time scale of emissions? Right? Because we see 495 and let's say 520, we measure them, but we don't usually measure the,
340.
yeah,
Yeah. So then what? What's your question?
so how do we know?
How do we know it's absorbed?
Yeah.
That's a good question. You mean how do we design experiments to know that, right?
Yeah.
Well, then you can what you can do is you can just add something absorb 340 in the solution. It doesn't have to, be in the fluorescent range, right? So, and you should be able to see less emission from that 495, the terbium. But this is a known effect in photochemistry, photophysics. It's called the inner filtering effect. Yeah. It's kind of like you get a screen before the terbium, and like it will definitely reduce the intensity, right? So if you have lower intensity, the emission gonna be weaker.
Yeah, I have a question about the quencher. But is the quencher is specific to some wavelengths, a range or can we find some quencher such as I have
Quenches everything.
Quencher, yeah. And
No. Quenching, so quenching is actually also an energy transfer process, right? So the reason we have FRET is because it matches this, the acceptor absorption matches the emission of your donor. So for quencher, you need to do exactly the same thing. The only difference is the quencher is not fluorescent. So basically absorb the emission, then just dissipate the energy through whatever, rotation or something like that. So with that being said, unless you have a quencher with very super broad absorption, otherwise it's gonna be specific. Yeah. But in general, you know, I remember there's a dye because one of the postdoc we work on, you know, some sort of near infrared dye, we try to quench that. And then I think there's a quencher called a Sudan black, something like that. So it's like black, you know, so it can just quench broadly. But you know, at the end of the day, you just want to make sure the quencher absorption matches the emission of your donor. Yeah. It's the same principle there. Okay. Then this alpha screen right now, we don't have this capability on the H1. I'm thinking to get this on the new reader. So what is alpha screen? Alpha screen is kind of interesting. So basically what it does is you know, you have a laser source, right? And you excite a photosensitizer. And then with that photosensitizer, because we have oxygen in solution, right? Photosensitizer can convert oxygen from so-called triplet state to the singlet state. Singlet state oxygen is highly reactive. And then the singlet oxygen is gonna diffuse away from the donor bead to the acceptor bead. And so the radius, I think for the diffusion is about, I think 100 nanometers or something like that. So it's definitely longer than FRET, you know, than nanobread, but still has a defined radius, right? So then if your acceptor bead is within that range, and it's gonna react and, you know, generate a emission essentially there, right? So it's also ratiometric. But I think I talked to some people who run this assay. This assay is kind of tricky actually. It's all the beads are photosensitive, so you need to run this in the dark. You know, so we probably, if you really want to do this, we probably need to put this in the new cell culture pool, then I mean room, and close the door and, you know, like run everything in the dark. Yeah. But anyway, so they said this alpha screen is more sensitive than TR FRET. You know, so so we'll see. We haven't tried, but we will see. But you know, the downside for the alpha screen is it's a bead-based measurement, so it's not homogeneous measurement, and the interpretation there can be tricky, right? So, but anyway, you know, in terms of accessories right now, like injector is one thing. I think I really want to have, especially the measure kinetics. You can just, you know, start your reaction right away, right? And you know, for kinetics, for example, you have a 384 watt plates. If you have an injector, actually you can tell the plate reader to synchronize everything, right? So basically, you do the injection, you start reading, and do the second injection, start reading. So they all have the same time 0. But you know, when you inject manually by hand, you add everything to the plate, you start reading. But when you read the first well and the second well, the time is different already, right? To the last well. So that's why with injector, you can measure very accurate kinetics there. Yeah, that's right now we have this injector on Biotek. It's the dye volume is so large, it's essentially useless. I don't think they have planned to fix that. So, you know, on the other hand, the BMG has an injector with only 100 microliter dye volume. I heard it's easy to be clogged. So, you know, down the road, if you get the instrument, you guys use it, you want to be very, very careful. Once you use it, you want to, you know, rinse it very well, make sure it dried, right? So don't clog the tubing. Incubator, right? So H1 has a CO2 incubator. I don't think we can control the oxygen level, right? On that one, right? But BMG, the one, I think it can control both the CO2 and O2 level, so you can run hypoxia experiment if you want to. Yeah, But actually, in reality, I think you can always use this so-called what you add sodium bicarbonate to the culture medium, and just I think for 24 hours it should be okay, right? So it's a CO2 independent medium, something like that. Yeah, we talk about dual PMT. The reading pattern, right? So I don't know whether you guys remember this. The way Biotek H1 reads is actually it goes like, you know, from A1, A2, A3, like go horizontally to the end and then come back, right? Backwards from like B, what, like 12, B11, B10, you know, go this way, right? So this is the way it reads. Yeah, you guys know? No? Yeah, yeah. So I think some of the people been through this, we know, right, how painful this is. I mean, this means if you run kinetics assays, if you make your replicates on the, you know, in the columns, so your first well, then when you read the second one, that's already been, you know, through like separated by like 12, 24 wells, right? So I mean, I personally think that's really something should be changed. So the BMG system, I mean, part of the reason I think the feature we like is you can define how it reads, right? So you can define go horizontally, or you can go this way, you know, just like every time it's all from the start, from the first column. So you can define or go vertically, whatever. So you can define how it reads, the reading pattern. I think this is especially very important when you do kinetic assays. I mean, if you just do a endpoint assay, it's okay. But you know, also like ratiometric experiments, yeah, that can be critical. But anyway, I think this is something everyone should know, how plate reader works, right? How it reads. It's very interesting. You know, when I called Biotek, asked them, like they have service engineers, ask them how they read the pattern. Actually, this even the very high level service people didn't know. They have to like go back and ask. So yeah, it's yeah, they never think about these details. Okay, like I said, I really want everyone to be able to build from scratch, right? So don't just copy and say, hey, I copied this from wherever. No, that's not the way it should be. You need to understand all the parameters in the protocol, right? What is PMT? What is PMT? What is PMT? What? For the yeah, for the multiplier tubes, right? So what it determines? Anyi, do you know? The Z value? You mean the reading height? Why? Okay. Why? So what is PMT? It's photomultiplier tube, right? So what it does? What? Yeah, it basically just, you know, measure light intensity. That's it. So it cannot differentiate wavelengths. It can only count photons essentially, right? How many photons? It doesn't know what kind of color. That's called PMT. And you need to apply a voltage to PMT. The higher voltage you have, the higher sensitivity you're gonna have. But at the same time, the cost is you have higher noise, right? So that's, yeah. So in like the Gen 5, the software, there is a place you change the PMT voltage, right? So that's actually will basically change the voltage. You make it, you know, more sensitive or less sensitive. Yeah, it's called a gain. Yeah, but the gain is just related to PMT. Yeah, I mean the gain, yeah, it's just related to that voltage. Okay, so I hope everyone understands. Bin, you have questions? No? You know PMT?
So August.
What was the other one you mentioned? Because you said there's PMT and then there's what was the other one?
CCD.
CCD.
Yeah.
What's CCD.
CCD, coupled, what's the full name of CCD? I mean, it's just a camera, right? I mean,
Diode,
what?
something, diode,
Diode, right?
diode.
Yeah. Coupled camera, whatever, that's a good one. I think we should do this next time. Yeah, I mean, just in our camera, we have CCD, right? So. But anyway, what is?
Is that the charge couple device?
Okay, charge couple device, not diode.
Yes.
Yeah. Close. Yes, but in general, for all these optics, generally you use PMT just for sensitivity, and that's PMT is pretty good. Yeah, when I was a graduate student, we use those PMT. Actually, you can also cool down the PMT. You have a little thing, cool it down to like -20. You can reduce the noise, the electronic noise, and enhance the sensitivity that way.
There's an electron after switch, right?
Yeah,
Yeah,
they do that too.
That's what it to cool it down and increase
The sensitivity, yeah, something like that. But anyway. Yeah.
So each of these. So these call
In one or two.
Manual,
Yeah.
manual for sure. There are
Yeah.
always
Is
manual,
it
but nobody
how
reads it.
to view the protocol?
Include the build protocol, like examples.
Yeah.
Yeah, I mean, there are tons of build protocols, but then why, right? So I just want everyone to understand every step of that protocol. If you don't build by yourself, you just load it, you will never know. Right. So that's why I think we should understand every parameter in that protocol, so you can always build the protocol by yourself. I think one thing is we should recognize this is, I mean, we do biology, we do this, but my core expertise is still chemistry, right? So I want everyone in the group know how to develop assays. We are not just, brain dead following the protocol. We should be able to develop our own assay. We know how we can make the assay better, right? So that's my goal. That's why I want to talk about this. And there's another thing I really want you guys do, but just I always get ignored. I want to build a real-time data analysis pipeline. What it means, right? So a lot of times you run the experiments and then you just go home, do the analysis. But the problem is if you find a bad data point, right? And then you probably have to start over next day. You have to resolve your protein and just start over. If you can catch your problem on the day when you do the experiment, then you probably can just redo that right away with everything you have, assuming the incubation time is not like super long, right? So that's why I think to be able to analyze data in real time would be very helpful. And I mean, at least I know when I was a student, that really helped me a lot. I actually spent like a couple of weeks to write some scripts to analyze the data in real time. While I was collecting the data, I will be able to just generate those, publication quality figures, essentially, using a program. At least you can see whether it makes sense or not, right? If it doesn't make sense, or there's like 3 replicates, 1 replicate is way off, I mean, probably I have to just rerun one and then, get the data consistent. That happens. But then if you don't catch that, then you have to redo another day, and then you probably have to do another 3 replicates, right? So we should, yeah, I think we can talk about this. Maybe let's see with the new software or the new instrument, whether that will be helpful. Yeah, but I think we should definitely try to implement this. Another thing I really wanna push is we should store all the raw data in Prism, right? Instead of process data. I know it's easy, it's convenient to just use Excel, get a percentage whatsoever, but you can do the same thing in Prism. I know it's not as convenient as Excel. However, I think that would just actually make your life easier down the road, especially when you try to publish, right? So, that also helped me to troubleshoot your data if you have problems, especially like nanobread. A lot of times you just, or TR-Fry, you get a ratio, but ratio doesn't mean much if you don't look at the raw numbers, right? So do you have changes on the 495 signal or not? If you do, that means there's something wrong going on. You have to figure out why the 495 signal changes. But if you just give me the ratio, I don't really know, what it means. So I know now we, some of you guys have a good practice. You just paste the raw data in the weekly report. That's very helpful, actually. Help me to look at that. But then at the same time, I think if you just store that in Prism, that's also helpful too. The only problem I found is in Prism probably is, when for this kind of ratio data, how you should arrange them, and then how you can use Prism to do the calculation for the ratio. I haven't figured that out. So it's, yeah, in terms of that, it's a little bit stupid. They probably have something.
Well, I think the tricky part with the real-time analysis is, assigning different wells, because so often you're making experimenting different layouts, right? And so I know in the Gen 5 software, you can change which wells are assigned, like with wells standards, etc., and program those. But the Gen 5 software is a little bit more limited in what you can do with graphing and export. Like I know that Bonfang was playing with MATLAB. There's lots of amazing things you can do, but because you can't pre-configure, what yeah, so because the layout is often changing, really just taking the data and pasting it over is frequently the easiest way.
Okay, but then why not? Yes, I know we're saying like you're changing the layout. But if you say before you start your experiment, the day before, you plan your layout, right? Then tell your program, this is my layout for today. And then you generate data, you just get analyzed right away.
Everybody needs to be a data scientist to design your protocol.
No, not really.
Because why? Because you need for the data. Okay, you can write a script to organize this data, but to generate, okay, this column, they have some rows, we affect, just like Tommy said, okay, everybody may have different layouts. You have you from high compensation to lower. You from you set up different lines, different columns.
Yeah.
But that script will not work. So everybody needs to have specific little script to load your.
Yeah, I think people should know how to write these scripts.
So everybody needs to be a data scientist.
Okay, maybe too much to ask, but anyway, we can talk about this later.
Maybe someone should just write the script and give it to us.
You mean I write a script?
Yes.
You mean some homework? You know what? Actually, I did, right? But then you guys never used it. Remember, long time ago?
I remember.
I wrote the thing for your yeah, it was in MATLAB. Yeah, but then I was also able to directly say you got a play reader data, you can change it into a format, and then you can open directly in Prism. Actually, Prism had this open file format now. So basically, it's just like ASCII files, right? So you just put your data in there, and then when you click that as a Prism file, it will do all the analysis, everything. Yeah, plot it the way it's supposed to be. That can be done too. So just I feel like I spent time there, but nobody really care. Okay.
It's been a long time.
Yeah. But I feel why you guys want to use it, probably still you don't know how to change it, right? So if you change your format, then you found the program doesn't work, and then I'd rather just process by hand. But if you know how to change the program, then probably you will do it. Right. So it's like user friendly. I should make it user friendly. But anyway, we can discuss that later.
I've also noticed in Prism, even if we have raw data and other things in our Prism file, when we copy the graph into the PowerPoint, it only takes the data for that graph and not all the data that was in the original Prism file.
Really?
Yeah. So like if you double click the graph from your PowerPoint, you only get the data sets that are in the graph.
Yes.
So if you have other data, raw data that you're processing, like for the normalization and all these other things, you won't see those.
Are you sure? But if they're linked, so for example, you have a data table, you first do normalization, then you plot it, do the fitting.
Yeah.
You copy that graph, it should have everything from the raw data. That's my understanding.
Okay.
I mean, if you don't use Prism to do the normalization, say you have two tables, one is just normalized data, one is your raw data table. Yes, I mean it will only show up all the linked table.
Okay. Yeah, but I was just thinking in the case of like the ratios versus the actual all the data from the 340 and how we could get that into the report to see that there's
I hear you. I mean, like I said, that's maybe the problem right now with Prism, right? So it doesn't process this racial data very well.
I don't know what it says all the different possible that you can like
The first column divided by the second column.
yeah.
Yeah, something like that. But the problem there is we need to format our Excel data into that form. We should, I mean, doing that manually will be, too much. I think unless we have a program, sort of, you can.
Actually, there's a something like calculate between two tables and generate the third table like racial.
Really? Does it?
I use that for.
Are you sure? Okay. I mean, if they have that function, yes, then that will work easily.
So if you use the final result table to make a graph, and then you put it into the PowerPoint, we double click the graph. Can you see all these layers of processing?
Yeah, you should. Yeah, if they're all associated.
Yeah, that'd be good.
Anyway, I think that some of these solutions are more complex and probably difficult to apply universally. Because everyone, if they had a solution, would have a unique solution. So maybe there's some other solution, like we could take the Excel files and attach them somehow to the report or link them somehow, so that there's a copy of the raw data reports.
Yeah, that can be done too. But I mean, if like what Hanfeng mentioned, if you can use one table divided by another table, that solves the problem for the ratio. Right. But yeah, we need to look into that. I don't really think we can do that. But anyway. Yeah, because the last time I tried, I couldn't figure out. Maybe I was stupid. Okay. Here are a few things, right? So we want to really pay attention to. We already talked about the gain, right? Gain is the PMT voltage, essentially. It's highly relevant for fluorescence and luminescence. Do you care about gain for absorbance? No, because why you don't care about gain? Yeah, it's.
I did optimize the gain one time. once the signal is very low, if you change the gain, you will get a high number. Last week in my weekly, the Western blot sample, I do the envelope assay. The signal was around 100 and 200. If I change the gain to higher, the number will go to about a couple of hundred, but the background is the same. Yeah.
Okay, so then you get better signal to noise ratio.
Yes.
Yeah, that's possible. I mean, I think the noise you get is how to say, it's electronic noise. But I don't know, show us the data.
Okay.
Yeah,
There is no gain adjustment for the absorptions on the, so I see.
no, there's no, I mean, I mean, absorption is essentially what? I mean, it's a percentage of light getting absorbed, right? So you know your the incident light intensity, then you measure the light intensity after passing through the solution, then you do the ratio, that's your absorption. Right? So it doesn't matter. I mean, I guess they just use the highest gain to just make it as sensitive as possible. I don't know, yeah, but you definitely don't need to adjust that. Yeah. The reading heights, we talk about that. I really want everyone pay attention to this. You know, when you optimize your assay, you should know your you should do a scan with your defined volume, right? And this is highly dependent on the volume. Yeah. Top rate or bottom rate, right? So we already talked about this one. Yeah, crosstalk. I think this is another thing we haven't discussed. What is crosstalk? Crosstalk means you know, for example, you have, oh, can I draw here? And yeah, crosstalk. You know, when you have these wells, then you know, you think you're gonna detect from here, but the signal from these wells may also reach your detector, right? So that's so-called crosstalk. Yeah. Crosstalk happens a lot, especially for luminescence experiment. For fluorescence is a little bit better because you need the incident light, and then you know you have the emission light. But still, for you know, fluorescence, you may also have crosstalk. I think on the H1, everyone should just pay attention. H1 seems like have a pretty bad crosstalk. We don't really know it's like just because of the age of our instrument or just the way it is. I'm gonna talk to Biotek to see what's their spec in terms of crosstalk on H1. Yeah. So Harman, you know that?
If you have opaque plates,
Yeah, still.
okay, is it to do with the Z focus then? Like where is it?
Yes, definitely it has something to do with the Z focus, because if you think about this, if you have the Z lower, you will tend to have less light coming from other wells, right? So if you, I mean, ultimately stick your probe into the well, but at the same time, I think when you make the Z lower, you sacrifice your signal intensity there too. Yeah, so at the end of the day, this is a trade-off, but I just want you guys be aware you may have crosstalk. I think another thing is initially I realized how bad the crosstalk is. I think when Ryan tried to run a nanobreath experiment in 3D 4-well plates, and the crosstalk was horrible. You have, you know, one well here, and then you have PBS, and then you have another PBS. I think even the third one, but at least this one give you more than 10% or 20% of signal of the luminescence, even have PBS. Yeah. So yeah, that's, you know, like very bad, right? And then I think recently Ryan ran another static experiment using TR fret. And what he had was, you know, the top row here. He has one protein, right? So he has a protein like V1, then he has a control without V1, right? Then he has another one like the meat one, and this one has meat one, this one has no meat one, right? So essentially these two wells are exactly the same. They are just controlled with exactly the same composition there, but their ratio actually vary by at least 2 folds. Why? It's because here you have very strong energy transfer and then it just leak over here, but this one has very low signal. You don't have very much signal here. So it's definitely, it's a crosstalk. Yeah, I want you guys know, you know, you should be very careful when you use this, especially the small size plates like 384. Yeah, with this new instrument, what it does is, I think what it, you know, they have a aperture here, like just a ring with a little hole, right? So that will just restrict light from other wells coming into your detector. And that trick seems to work pretty well, right? Hanfeng, you try it.
Right. And well, 7-digit readout and neighboring well.
Wow. Yeah.
The domestic readings are also usually endpoint, right? So probably the terms of advantage of spacing with well now.
Well, yes, spacing wells. But then, you know, when you have 96 well, you want to run as many samples as possible. So sometimes it's not, it doesn't make sense to space them. I mean, it only depends on how many samples you have, right? And, but they also run nanobrad kinetics assay. So yeah, it's, I mean, crosstalk is definitely a problem. I think we should know and we should pay attention to this. And maybe what we should do is we should look at, you know, the H1 right now, how bad the crosstalk is in terms of different plate format. And we should know, you know, if we're running 384, you probably want to space them out. But I really hope they will fix this problem. But this is not the way it's supposed to be, right? But with that being said, if you really have, I mean, at the end of the day, say crosstalk is not really avoidable, then what you should do is, like, you know, when you have when you arrange the samples, you should arrange them in a way, you know, say this is your 0 concentration control, right? Then you should have low concentration, like concentration gradient going this way instead of this one is your top, right? So then you go this way. I know it's easy to dilute this way, but then your top right next to your background 0, you may have like crosstalk, you raise your 0 a lot, right? So I'd rather just do the 0 at the end of the plate. So this kind of consideration we should pay attention to.
It's kind of like you include a little bit of for not good to the
To lower. Well, I mean, based on what Ryan showed, actually, he has higher nanobrad here, and then the signal on the background higher, and he has a lot lower signal here. The signal here is lower, so definitely there's like crosstalk with TR breadth. Yeah, so these two wells are exactly the same.
I actually had a note regarding the H1 that everyone in the lab followed that we're getting the elevated temperature experiments.
Oh yeah, that's
If
another.
you do that experiment at 37, once that experiment is over, the plate reader will stay at 37. It'll maintain the temperature of the last experiment protocol. So all you, and it takes a long time actually
To cool down.
Yeah, like 2.5, it goes from 37 to 25, it takes 2.5 hours.
Nice.
So all we need to do actually is at the end of the protocol, to change the incubation temperature back.
to room
to-
temp,
to
yeah,
25.
yeah,
And then you can just leave it,
okay. Yeah, that's something we should pay attention to, right? The temperature, when you set the temperature, you wanna be considerable for other people.
yeah, and you can even put that in your protocol.
Yeah.
Incubated 25, that's the last step.
Yeah, yeah, yeah.
Take the temperature back. because
Yeah.
If you run a protocol at 37 and do nothing, then the instrumental.
Gonna stay, yeah.
The next experiment. Changes the temperature.
Yeah, yeah. It doesn't have active cooling, I think. Well, but no, it's helpful in terms of, say, on this day, you run this, you set it at 25, you go home, right? At the end of the experiment, in the evening, it become room temperature. But next day, people use it, become a room temperature. I think what Harman is saying is if you don't do this last step, next day when you come in, it's still 37 degrees. No?
If you set up your experiment on 30 minutes after another visit,
Uh-huh.
so yeah, it's going to take a long time. So I think I want to be prepared for their own environment instead of blaming others. That you set the temperature too high, which is inspired.
Okay.
27 to 25, I don't think it takes 2 hours to print. Our room temperature.
No, that's really there for 2 hours. Yeah.
Yeah. And I did it, like, there was one time that I started my experiment immediately after the first issue out of 37. And then I knew I was gonna wait, right? But yeah, the time before that, the experiment was, much further behind and still it was at the set on 37. So I had to run the tool automatically back to room temperature if you run a protocol, that protocol ends, it's gonna maintain that.
Okay. Yeah, that'll be a good idea. Yeah. People come, yeah. Yes, I think that's a good point.
Can we add a stage to fix at lower temperature?
Yeah, no, Harman said at the end, yeah, you can do that.
Be able to add a stage to a lower.
But again, that will, I mean, the next person is still gonna take time. It just, take time to wait it to cool down. So I guess the point here is if we run a high temperature assay, yeah, we need to coordinate. But when we have more plate readers, this wouldn't be an issue. Right? So
It's actually not so bad, because actually when we book the time, we don't frequently book it back to back. I don't see
Yeah.
that too often.
yeah,
But if it stays there at 37.
yeah, then that
For a day, that's different.
yeah, that's bad for optics also. Yeah, okay, that's a very good point. Yeah. So we talk about the crosstalk. Any other questions? No. We talk about crosstalk. We talk about reading pattern, right? So that's all good. Any questions? No. Okay. And then here are also some details about microplates. I just realized I think we should, discuss this. There are many different kinds of microplates, right? So, and don't just grab one and assume that's the one you need. And there are so many tricks. The surface chemistry is the first thing you should pay attention to, right? So especially when you run enzymatic assay and the enzyme concentration can be pretty low, like in the nanomolar range. And if you use a so-called cell culture plate, for example, your enzyme probably gonna stack to the polylysine surface, right? So That's why for biochemical assay, we always buy this kind of so-called non-binding surface, the NBS surface, right? So then basically, when you run this kind of assay, you make sure that's NBS. You don't want to waste your protein by using a random plate. So I think we should organize the plates in a better way, or at least people should know what they are, right? So you want to pay attention this NBS. And there are also tissue culture treated plates for adherent cells. And for that, you have to, it had to be sterile, and I don't have to emphasize that, but I think for the biochemical assay, you want to make sure it's NBS. And then there are like black plates, white plates, or transparent plates. What they are for. You guys know, like, why we have black plates.
No, wait, that's why we have one.
Yeah. Black. Why we have black?
Black is for the luminescence. No,
Yes,
no,
black is,
white.
yeah.
Okay, I can get it back.
So black basically try to avoid crosstalk, right? So black absorbs everything, so it try to avoid a crosstalk. So crosstalk, I think I forgot to mention, there are two ways of crosstalk, right? So one is like we mentioned, you can have like detector here, crosstalk like here, right? Directly light up there. But it can also have this so-called through well crosstalk. Light can also leak through here. There's no way to adjust the Z height to avoid this crosswell crosstalk. The only way to avoid that is actually you have a black plate, like completely block the light. So that's why, yeah. But then at the same time, black plates, you're gonna sacrifice your sensitivity because it doesn't reflect light very well. Yeah. Yes. So, yeah, because if you think this way, with fluorescence, you excite. Well, maybe it's too messy. So with fluorescence, you excite, then you emit, right? When you emit, you can emit like all different directions this way, right? If you have a black plate, all these ones gonna be absorbed by the plate. Only this one gonna be detected. But if you have a white plate, on the other hand, this light gonna be reflected, right? Go back to the detector. So that's why white plate gonna give you higher sensitivity, but black plate gonna give you, better like crosstalk. I mean, like avoiding crosstalk. Right? So but then transparent plate is the cheapest one. I think generally it's useful for cell culture, but for a lot of our like high density assays like 3D, the black or white will be a better choice.
So the white or
Not completely, not as good as black, I should say, but definitely it's better than transparent for sure. Yeah. I mean, at the end of the day, it all depends on, how bad the instrument is, right? So that's why I think we should do some testing on these instruments and with different kinds of plates like white or black and try to see the crosstalk, how bad that is. I think that's no, it won't be transparent, right? Yeah, so that's why you can buy those bottom transparent ones. So yeah, it can be black or opaque or white, right? But then the bottom is transparent. And there are also different kinds of these bottom transparent ones. You can have the regular transparent polystyrene. You can have this so-called optical clear, which is transparent to UV. And then you can buy those 100 micron thick plate. So you know, basically it will be a lot better. 100 micron, yeah. The plastic, you know, the transparency is a lot better.
What is that for the cost of, I mean, can you use them for?
If they crosstalk, what I mean,
Can we use the blood tech for nanometer?
Yeah, bread.
yeah, you can, yes.
The many breads we use to actually increase availability to the beginning of the recipe, but if it is too strong, we can actually use the black.
Black, yeah. I mean, yes,
Okay.
we can, yes.
Most of the time we use the white tech, but. Probably the white.
I mean, at the end of the day, I think it's all about a trade-off of sensitivity and crosstalk. Yeah, I think for the TR fret we use white. Xiaoli, you test it, right? And
Oh, you can use it.
Yeah.
That's the uniform.
Yeah.
White.
but I believe you compare the black or Wenhao compare the black and white. But I don't really know whether he compared the crosstalk. I mean, you can get signal, but then the signal
No.
20. Yeah, I think for 384 he just did it 20. Yeah. Yeah. Oh.
The composition of wells that are next to each other are the same, like let's say replicates. Crosstalk between replicates, if they have the same composition, probably won't change the data much. Or
Yeah, replicate is a particular thing. It was for me, I first. Yeah, they are fine because they are at same level. No, the terrible thing for crosstalk is that high intensity affects the lower. So this will increase the, suppose I said TBS, it should be zero, but the idea as but with the crosstalk, you have a neighbor well very high, such as 2000. TBS should be zero, but crosstalk is a chain, maybe 2000 to the TBS. So this will supposedly make your drug less potent.
what about and with little.
The one in the middle is half more further from neighboring.
Well, I don't know, I haven't noticed this, and that's, usually I'll do 3 replicates in a column and then space 1 column, 3 replicates in a column. I do it that way because I used to create more of the multi-channel. This is designed for the 296. But I don't really know this.
I mean, you haven't looked at that.
I haven't
right?
looked for it
Yeah,
specifically.
exactly.
Yeah.
So I mean, I think all these observations I came up with through like, you know, the data from our weekly reports. And, you know, like for example, Ryan asked me this question, I thought about it, this crosstalk. So
Maybe we need some mechanism for deposit, like a depository for our raw data. Where you can
give me more homework.
Well, it's just, I mean, it's just an Excel file. It's fascinating.
Yeah, that's true. Yeah, I mean, you guys should store all those, you know, Excel file and the instrument Biotek files too. Okay, good in terms of bottom. I mean, you just want to be very careful in terms of, you know, selecting your plates, right? 3, should we, I mean, say, you know, down the road, the new reader we are gonna have a 1536 capability. So, you know, then the well density gonna be even higher, right? So yeah, you probably cannot pipette by yourself. You need some sort of liquid handling instrument to do that. Don't worry. Yeah. What? Yeah, as a team, like 4 people take turns. So, but when you have very small volume, evaporation can be a serious problem, right? So I think that's something everyone should pay attention to, especially if you want to run a, say long incubation experiment, or running kinetics. I think it's a good practice to seal the surface. Sorry, let me take this. Oh, stupid people like are trying to install change to an internet company but anyway, evaporation problem. I think it's good practice to use those film to seal that. I mean, we also have a sealer like the SEH group commonly use right downstairs. I mean, you can have transparent ones. Yeah, technically, but they also sell those you just like sticky ones, right? And with optical transparency. You can seal that. I think that's, or add a lid at least. Well,
Do we have any of the Biotek or the shiny stickers for the plates to buy? Like, I don't know.
yeah. It's aluminum foil. You can buy those aluminum foil ones.
Yeah, we have them there.
Yeah, opaque.
I also looked at them.
Do anybody know where the aluminum foil is to seal the plate? You have one?
I have one bag.
You have one bag? Okay, so she's the right person. But anyway, I mean, the thing is, just be careful when you go with like 20 microliter or something like that, right? Even like smaller volume. So the thing is, this is probably want to hear you guys' opinion too. I think the other day, Min run the assay with like the collaborator at Rice, right? So what you guys did, 3 to 4 well place, you seal the top and then you read from bottom. Looks like data is pretty nice. So I'm thinking, especially like they're running a kinetics experiment, they used to have this baseline drifting problem, signal, even the control going up all the time. I guess that's probably evaporation. You just concentrate the dye. Right. So, with that being said, I guess with this kind of kinetic assay, maybe it's worthwhile to have, the film on the top and then you have optical clear bottom, 100 micron, like thick plate. So then that will give you maximum signal, but you still do a bottom rate there. So the plate you use was just regular. It's transparent, but it's not optical clear. It's still thick, right? So, but you can buy those like super thin bottom, and you should be able to get like better signal to noise.
There's an optical for the plate, it will be very, very
Expensive. Yeah, well, let's see. I know that
we call the glass power glass water. It's very fragile.
Well, let's see how
We use
expensive
it
they
for
are.
alcohol or other.
they're like, I mean, considering the protein we use, those are maybe, I don't know, $50 each plate. 100, really? They're scaring me. Okay, we'll check, but at least I think my point here is maybe it's a good practice. We just for low volume, we seal the top and then read from bottom instead of going from top.
The general thing about it should be fine.
Yeah, we can, yeah, clear bottom. But we can test and see how it goes. Yeah.
Are there any reusable glass?
Wash them.
Wash
Yeah, maybe. I don't know. Yeah, the thing is, if you think about this, like the protein, the reagents we use, the time we spend on this, it's like the one plate is nothing. Like so, I think whatever. I mean, my point is we should get the best data we can get. At least for now, we don't worry too much. But maybe next year we start to worry about money.
They make boards, microboards.
They do. Yeah.
It is.
They also make those full cores microplate, but then you have to reuse them. Those are pretty expensive, $700 each. No, maybe like 1,000 something. Actually, I looked it up before. They have whole cores, 96, at least 96. I'm not sure about 384.
I always used to feel so guilty if I dropped it.
Oh yeah.
That drop more.
Yep. And you can also buy Teflon plates too, reusable. Yeah. Okay, another thing I just want to mention is we also use this. I mean, we use a lot of 384 valve plates, right? But 384 actually you can go lower volume. Ran did some tests with his protein concentration was so high, right? So he tried to lower the volume, and you were able to go down to what, 5 microliter in 384, but without adjusting the Z.
Yeah.
You should if you adjust the Z value, probably you can get better signal to noise. Yeah, but the plate you use it has a round bottom, right? Are you sure?
Yeah, it's normal 284 wheels. The white one and this one is flat bottom.
It's flat bottom. Okay. But then your 5 microliter may not cover the bottom.
I tried with a colored liquid, 2 microliters and cover the bottom.
Oh, okay. So 5 should be definitely sufficient to cover the whole thing.
2 microliters, you need to shake it and will cover the bottom.
Oh, okay. So that's good to know, right? So everyone, you don't have to use like 1536. You can use 384 and you can go down to 5 microliters.
Cover the bottom, but it forms like a curvy.
Yeah, meniscus.
Yes,
So good.
you should. But you can see there is a color all of the bottom.
That's why.
Covering all the bottom of this color with 14 then not use 2 microliters. 5 microliters is not enough to cover.
Yeah, 5 will be safer. Yeah. Well, there's another plate, 384. What you can buy is if you don't plan to do the bottom read, right? So you can buy this round shape 384. So for that, your drop is gonna go in here and you form actually a thicker liquid if you use 5 microliter, right? So that's another possibility. But with this kind of round bottom, you have to do top read. You cannot do bottom read. Yeah. That's the thing. But anyway, these are all the possibilities, especially when you want to reduce the volume of your assay. So Ran, you did for that, it was not transparent on the bottom, so you all did top read, right? Yeah. Okay. Got it. But then do you know you have evaporation problem or not?
I not never reach, but in my experiment, I usually use 8 microliter and do it after 4 hours. I didn't see very clearly change.
On the 495 signal.
Yeah.
So that's a good sign. Yeah. Okay. Good. Yeah, we talk about place sealer. Wow, there's a lot of stuff going on. Okay, this is my last slide. But I really wanna, I don't know, what you guys feel. I think that's good discussion. Yeah. Okay. Yeah, how we design an assay, right? So when we design an assay, it's important to have positive and negative controls. So positive means that's something like when it works, right? So negative means that's your sort of background. And also when you design assays, especially like biochemical assay or any kind of assay, there can be non-specific interactions. So very weak interactions happen everywhere. You need to think about how you design a control to subtract that non-specific interaction. Right. So I said I want to give an example on the EF7 assay. Let me think what I want to talk about. But maybe I'll go with the TR-FRET one first. So TR-FRET, I think everyone does that, right? Right now, a lot of people do that. For example, we take the BTK, his BTK as the example, and we use this terbium anti-his to label BTK, and then you add a tracer, right? So with this, you are able to design, like you can titrate the tracer. For the background, what we do here is right now at least, right? So we remove this BTK, we look at this non-specific interaction between tracer and the his. We define that as a background. But let me ask you, what will be an alternative background? And so what if the tracer not only has a non-specific interaction to the antibody, but also has a non-specific interaction to the BTK? How can you subtract that? GST BTK. So what if tracer has non-specific interaction with the BTK portion? Well, yeah, that's one thing. But I mean, you see signal, so bin. Exactly. Yes. Right. So alternative control here is if you have a known inhibitor that will occupy the tracer pocket, the pocket tracer binds to, you add that high concentration, that compound, and assuming you can block 100%, and the signal you read there will be your background, right? That will count everything binding to tracer, binding to the BTK. Harmon.
Is that a circumstance in which we would observe a hook effect as the original receptor site is saturated?
You mean original side of the site is saturated?
There's an allosteric binding site for the tracer in addition to the primary binding site. That's the scenario.
Yeah, possibly.
So yeah.
I mean, those allosteric is maybe many allosteric, right?
Lex just said hook effect. I like it, so I wanted to go back to that.
You mean, are we gonna see hook effect?
Yeah.
That's a good question.
And also, like, what is hook effect? So you saturate the binding, and then something happens, right? What is that? Nice. I don't know.
Yeah.
Yeah, so your tracer can bind two pockets, right?
For example, yes.
Yeah. So, but you want your target is only one or two pockets.
Yeah.
So now you want to use another inhibitor to bind the other pocket.
The original pocket, yes.
But if another pocket can affect the output of the allosteric.
Oh, that's that. Yes, then that would be too complicated. I'm talking about now. I mean, you can call that allosteric binding, but most likely it's non-specific binding due to hydrophobicity. So it's just like, slap on the protein. That happens all the time, right? If you especially give a high concentration tracer. Yeah, that's why, I mean, another thing we just talked about the inner filtering effect, right? So if you give very high concentration tracer, you may have the inner filtering effect. That's why you need to have a tracer that binds tightly to your target. That will be beneficial.
Are we always looking at non-specific binding, or is there a point at which collisions happen so frequently that we observe them on the time scale at high concentration?
Yes, I think Hanfeng and I did some calculations. Only when you go up to like millimolar concentration, and they will have what? High micromole, yeah, high micromole. And then the distance between molecules will be on the scale of this energy transfer circuit R0 value.
Yeah.
But the concentration range we work around is like too low. Yeah, it essentially won't happen. Yeah. Yeah, I mean, yeah, we thought about this before too. Okay, so this is one assay design, right? But at the same time, you can just directly label your BTK with terbium. That's direct labeling. You don't have the antibody. So in this case, if you have the tracer for the negative control, then you can only use the inhibitor to saturate that pocket, right, as your negative control. And then the tracer, whatever signal you're gonna generate, that'll be the non-specific binding. Okay. Yeah, I think that's something we should pay attention to. And yeah, I forgot what I want to talk about on the EF7 assay. EF7 is a kinetic assay. But anyway, maybe when I remember, I'll let you guys know. No, the background. Oh, yeah, now I remember. Okay. Getting old. EF7. EF7 is the substrate, right? Then we will generate a floor for like the coumarin. So, one thing, when you establish this kind of assay, like enzymatic assay, what you really want to do is you want to have a sense, it would be nice actually you have both the substrate and the product as a pure compound. So then when you design the assay, say if you add 1 micromolar of this thing, and you can also add 1 micromolar of this coumarin, do a standard curve there, right? So then when you see, say 500 signal, that will correspond to whatever concentration of coumarin, your conversion here, right? So I think it's a good practice when you design this kind of fluorogenic assay, right? So, and also that when you use a product to set up the protocol, what kind of PMT you want to use, because you don't want to overflow the instrument, right? So you want to make sure you are in the right range. That's actually, yeah, what I want to say.
Especially true for the imaging.
Mhm.
The imaging, since it's high throughput, if you have some wells very weak, some wells are very strong,
Mhm.
use the weak well to set up the connection. You will
And
see
just overflow
yeah,
everything.
nothing.
Yeah, exactly. Yeah. But anyway, I think my point here is when you design an assay, when you run an assay, and think about all these points, right? Think about the positive control, negative control. You should, the biology experiment, if you don't have control, that's like means nothing, right? So it's not like chemistry. You run a reaction, you get a product, you run an MR and say, hey, that's my product. no one can argue with you. But you know, with biology, you get a signal, but what if it's non-specific, right? So that's why biology is so complicated. But anyway, that's all I have. Do you guys have any questions? No? Yeah, I think it's no, but what? Oh, Lex, what's your question? The what? What's the last item? What? Food. No, not today. I was recording.